You're on the Argument video channel, Real Analysis video series, lecture 10, all about the rearrangement theorem. So let's begin. Let's look at what we were doing last time. So we had a sequence equal to k equals 1 to infinity, negative 1, k plus 1 over k. And that would end up looking like 1 minus 1/2 plus 1/3 minus 1/4, and so on. And this is conditionally convergent. From our 2s equals s implies 2 equals 1 proof. Not really a proof. We just showed a contradiction so that I showed it must converge to the same value. So proposition, let's do a formal proof of that for all for more general sequences. Every rearrangement of an absolutely convergent series converges to the same limit. Series converges to the same limit. Okay. Proof. So let an be absolutely convergent, so along two words, and let pi be a permutation of the natural numbers. Suppose it converges to L, then we know it also converges absolutely. So now let epsilon greater than 0 by the Cauchy equivalences we saw last lecture. There's a natural number such that the sum from I equals n plus 1 of the terms, absolute value, is less than or equal to something. We'll fill this in later to make our proof look nice. So now choose m equals just any m greater than or equal to n, such that a1, a2, all the way up to an appear in a pi 1, a pi 2, and all the way to a pi m. So now suppose m greater than or equal to m. So now if you take the sum of I equals 1 to m of the rearrangement, make that more legible, and subtract off the limit, that's less than or equal to I equals 1 m minus that should be at infinity, ai oh no, we're not substituting n, we're subtracting and adding terms here, so that goes n I equals 1 ai plus n I equals 1 minus l, absolute value, and then group those. So we're still in it, that's an equality. Now we use the triangle inequality and get this. Oh, whoops, forgot to write that there. A pi I. Plus, I forgot to write it there as well. That should be a AI. N of AI minus L is, if you apply the triangle inequality again, you got this, n plus 1 ai plus I equals n plus 1 ai, or to infinity. So you're applying this triangle inequality to every term in the sum in both inequalities. So now we have two things added together and we want to make it epsilon in the end. And we have this inequality up above. And we just fill that in so it looks nice in the end. So that completes the proof. So, whoa. Why is my screen dark all of a sudden? Okay, let's just keep going. Looks kind of cool, I guess. So, a pi I equals 1 to infinity converges to L. So it's the same limit no matter what rearrangement you do. Alright, now let's look at what this means. So a couple remarks. So if you have a series where everything is non-negative and Sn is the partial sum we defined last video, and Sn is thus increasing because it's monotone increasing, at least, not always increasing, is monotone increasing since an greater than or equal to 0. So 1, if Sn is bounded, then that means that since it's monotone increasing and bounded, this sum converges by the monotone convergence theorem. Converges by monotone convergence theorem. If it's not bounded, then it just goes to infinity, and yeah, it doesn't converge, it diverges, and that's it. Now we're looking at a theorem, the main topic of this lecture, called the rearrangement theorem. It's a bit of a hairy proof, so watch out, but we'll get through it. Its statement is if that is conditionally convergent, so it converges but not absolutely convergent, then for all L in the reals, there's a permutation such that that is L. So you can rearrange a conditionally convergent series to get any real number. So in the previous case, we got that it would always converge to the same number. In this case of conditionally convergent, it can converge to any real number. So let's start. Suppose that is conditionally convergent. Let B1, B2, and so on be the positive terms, and C1, C2, and so on be the negative terms. The zeros don't really matter because they end up being, they don't contribute to the sum at all. As we showed there in the remark, since this is, everything here is positive, then the partial sum of these will converge by the Meissner convergence theorem. So if Bn converges and Cn converges absolutely, then An is equal to Bn minus Cn is conditionally no, actually it would converge absolutely. If you take an absolute value in there, it would just converge. So that's a contradiction for Bn converging and the absolute values of Cn's converging. Now suppose, so that's a contradiction. I'll just highlight the part that's a contradiction. So that can't be true. So now, whoops. Suppose Bn diverges, but Cn converges to some m. Then for any r greater than 0, there's an n and n such that k is greater than r plus m, right? So for k large enough, b1, b2 up to bn occur in a1, a2 up to ak. So we get that you take this sum, the partial sum, then that will just be the sum of the bi's up to n and the sum of the ci's with an absolute. It's greater than or equal to that. And from the previous inequalities, we get that that is greater than or equal to r plus m minus m equals r. Therefore, an would also be unbounded. Another contradiction. So we're just eliminating cases we can be in at this point. So I'm going to highlight that, but I won't connect the two. So that's another contradiction. Let me just write that. Contradiction 1. And this is contradiction 2. Okay. Now let L in, there's another contradiction coming up. We need to eliminate another case where the B's converge, but the absolute values of the CN's don't converge. If sigma Bn equals m and that equals infinity, then that would imply sigma Bn equals, then if you follow a similar path for this contradiction 2, we would end up with a contradiction. So highlight that. Contradiction 3. So we've eliminated the fact that they both converge, eliminated the fact that only one of them would converge. So that means they both must diverge. And we'll see how that ends up with us getting any real number. So that must be diverging, and same with this. Now let L in reals, let M1 be least integer such that B1 plus all the way to BM1 is greater than L, and N1 be least, just gonna put integer there, or index, such that B1, C1 and if we subtract all the C1s from the B1s up here, then let's call this U1, so that just means short for upper, so since it's above L. So U1 plus C1 plus all the way to CN1. Because these are negative, this will eventually go to L. And then let M2 be such that U2 is equal to, just call it, so that's U, we'll call this V, the next letter, V1 plus BM plus 1 plus all the way up to BM2 greater than L, let N2 be, what were we trying to say? U2 plus CN1 plus 1. Yep, we need an index on this one. Forgot that. Plus all the way up to B and 2 that we're finding is less than L. And if you just repeat this for any k, we have that U sub k is equal to the sum n plus k from I equals 1 bi plus I equals 1 n plus k minus 1 ci is greater than L and is greater than, and that is greater than bk. Mk I equals 1 b I plus I equals 1 n k of ci, and that's just vk exactly. So we're just saying we're gonna repeat this process over and over again. So now we're gonna claim that this rearrangement will give us L, the real number we defined above, let L in R. So B1 plus all the way to BM1 plus C1 plus all the way to CN1 plus BM1 plus 1 is kind of tedious if you can't tell, but we'll just do it. For math, CN1 plus 1 plus all the way to C2 and so on will equal L. Then we have that UK minus BMK is less than or equal to L, which is less than UK by definition, and VK, is less than L, which is less than or equal to BK minus CNK. Note that the ANs go to 0, therefore the BNs, and that's because since this is convergent, and we said last lecture that if it's convergent, then these terms in the sequence must converge to 0. So then those go to 0, and these go to 0. And then L plus CNK less than or equal to VK less than L less than UK less than or equal to L plus BMK. So this must go to L, and this must go to L. And so we have this thing, we have the L squeezed in by two terms going to L. So then so the VK is squeezed in there and the UK is squeezed in there, and the other sides go to L. By the squeeze theorem, BK, UK must go to L. And that is almost it. Now let Sk be the kth partial sum of this rearrangement. Then we have that Vi minus 1 is less than or equal to Sk, and that's less than or equal to Ui. Or that Vi is less than or equal to Sk less than or equal to Ui. Thus, by the squeeze theorem, since both sides of these go to K, Sk itself must go to K, or go to L. I'm mixing up all of these letters. Okay, phew. That was very tedious. So first we had to eliminate cases. So we partitioned the terms based on being positive or negative. So B's are the positives, C's are the negatives. Then we concluded through contradiction that if you sum all the positive terms, it diverges, and if you sum all the negative terms, when you absolute value them, it also diverges. Then we built up these indices M1, N1, M2, N2 to oscillate around L. So U1 would be greater than L, V1 would be less than L, and then U2 would be something after all these B1s and C1s, and that would be greater than L, and then make that less than L. And you repeat this for all K, because it's an infinite series, infinite sequence. Then we use the squeeze theorem to show that these VKs, UKs, which oscillate around L, actually go to L. And as a final step in the proof, we gave up explicit rearrangement and showed that this partial sum of this rearrangement itself goes to L. Thus, we can get any real number out of a rearrangement of a conditionally convergent series. And that's it.